All right, let's go with some questions from Unit 2 exam. Okay, so the first question, what is the molecular formula for compound X? So we are given the line structure. We need to convert that to a Lewis structure to get the molecular formula. So N's and Ben's are carbon atoms. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon atoms. Therefore, option C and D are out. And then hydrogens is the only difference between options A and B. If we count the hydrogens now, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hydrogens. Okay, the idea is we added carbon hydrogen bonds to fulfill the common bonding pattern of 4 for carbon atoms. Okay, so we had, if you had only one bond between carbon and nitrogen, like in this case, we needed to add 3 more carbon hydrogen bonds to fulfill the common bonding pattern of carbon. So anyway, so we have 13 hydrogens. Therefore, the correct answer must be option A. Moving on. How many lone pairs of electrons are on this molecule? Okay, so when it comes to lone pairs, let me try to get rid of what I just did here. Okay, so lone pairs are about fulfilling the octet of each element. So we have nitrogen. We have 3 bonds around it right now, meaning 6 electrons. Therefore, we need 1 lone pair so that we can have 8 electrons around it. And same thing with this oxygen, we have 2 bonds, meaning 4 electrons. Therefore, we are going to need 4 more electrons. Therefore, we're going to add 2 lone pairs. Same thing with the other oxygen as well. We have 2 bonds, meaning 4 electrons. So we need 4 more electrons. That means 2 lone pairs to get that. So we see that we have 1, 2, 3, 4, 5 lone pairs. Therefore, the correct answer is option D. Okay. So that is that. And moving on to question 3. What is true of the kinetic energy of delocalized electrons when a substance has resonance, such as in the ring structure in the molecule above? So if we have delocalization of electrons, okay, it doesn't matter whether it's bond forming or resonance or whatever, delocalization of electrons mean the electrons have more space to move around. When the electrons have more space to move around, they slow down, therefore the kinetic energy decreases. So option A says the electrons can occupy a larger volume, which reduces the kinetic energy. That is absolutely correct. And then option B, the electrons can occupy a smaller volume. No, the electrons can occupy a larger volume, which increases the kinetic energy. That is not correct. The correct answer is option A. Okay. And moving on to question 4, hydrogen peroxide is often incorrectly used to treat sunburns. What is the likely Lewis structure of H2O2? So option A, I'm gonna discard that right away. Why? Because we have a hydrogen with 2 bonds. Hydrogen usually forms 1 bond. Okay, so because if it has 2 bonds, that means we have 4 electrons around it. The valence shell, the valence shell of hydrogen is the first shell, which can only accommodate 2 electrons. Therefore, 2 bonds are not possible. And then when it comes to option B, we see that on oxygen, we have 1 lone pair and 2 bonding electron pairs, meaning 6 electrons. We do not have 8 electrons around it. Therefore, that structure is out as well. Option C, hydrogen has 2 electrons around it, and oxygen has 1, 2 lone pairs and then 2 bonding electron pairs, meaning altogether 4 electron pairs, 8 electrons. Therefore, option C looks very nice. Option D, we have so when it comes to option D, we see that we have an octet around each atom, but we see that we have violated the common bonding pattern of oxygen. But still, the main reason is if we have hydrogen has 1 valence electron, we have 2 of them, that means 2 electrons. and oxygen has 6 valence electrons. We have 2 of them. That means 2 times 6, 12 electrons. Altogether, we have 14 electrons, meaning 7 electron pairs. If we count the electron pairs in this molecule, we have 1, 2, 3, 4, 5, 6. Only 12 six electron pairs, meaning only 12 electrons. So we have destroyed 2 electrons when we came up with this structure. That is not allowed. We cannot destroy the electrons when we come up with the Lewis structures. Therefore, option D is out as well. All right, moving on to question 5. So let's see if I can get rid of these first. Okay, in question 5, a substance is found to have these percentages of carbon, hydrogen, and oxygen, and its mass spectrum is shown to the right. What are the empirical and molecular formulas of this compound? Okay, so first the empirical formula, and then the molecular formula. Okay, so first of all, what we can do is we see that all these compounds have different molecular formulas. Okay, there could be only one correct molecular formula that should be based on this molar mass over here, which is around 85, 86 grams per mole. Okay, and if you think about, let's start with option D. Okay, option D has 3 carbons, 3 times 12, plus 6 hydrogens, that is 6 times 1, plus 3 oxygens, meaning 3 times 16. Okay, if we add this up, this is 36 plus 6 plus 48, and that comes out to be let's see, 78 78 84 90. This is definitely, the molar mass here is definitely less than 90 according to the mass spectrum. Therefore, option D is out. Okay, and when it comes to option C, we see that we have C2H3O. And C2H3O, that means 2 times 12 plus 3 times 1 plus 16. This is 24 plus 3 plus 16, which is less than 86. Okay, so 24, 27, 37, 43. This is just half of it. So because we don't have the correct molar mass here, and this is out as well. And if you go with options B and A, they have very similar molar masses. But when it comes to option B, the molar mass is not 86. I think it's, let's try this. Okay, so we have 4 times 12 for 4 carbons, and 8 times 1 for the 8 hydrogens, and 2 times 16 for the oxygens. We have 48 plus 8 plus 32. So that's going to be 48, 78, 80, 88. It's going to be 88, which is not 86. So for that reason, I would eliminate that as well. And when it comes to this molecular formula, it has to be, a second, it has to be 86, because it has 2 less hydrogens than option B, and that's a perfect match. And also C2H3O matches with that as well. The other way to do that is you can actually calculate the molecular formula, okay, and to arrive at the same answer. And if you do that, you should get the same answer as well. And how do we do that? When it comes to carbon, out of 86, 55.8% is the mass of carbon, and this is in grams, and divide that by the molar mass of carbon, which is 12 grams per mole. Okay, you're gonna get the moles of carbon, which is around 4. Okay, And then when it comes to hydrogen, maybe this is the only thing you have to do there. The 1 mole of this compound is 86 grams, and out of that, 7% is the mass of hydrogen. Divide that by the molar mass of hydrogen, which is 1 gram per mole. You're going to get the moles of hydrogen in 1 mole of this compound. You see that it is going to be, if you plug and chuck these numbers, that's going to be something close to 7 times 6, 2, 4, 8, 56, 60, around 6. Okay, so that shows us that our molecular formula should have 4 carbons and 6 hydrogens. Therefore, we can eliminate option B, and we are left with only option A. Okay, so that's the other way of tackling this problem. Okay, now moving on to question 6. What is true of the kinetic and potential energies of electrons when light is emitted? When the light is emitted, the electrons are moving from a high energy levels to low energy levels. Okay, if you can recall, give me a second, I need the pen here. If you can recall the Bohr model, okay, so what is happening in emission is, so we have these orbits over here and so forth. The electron is coming from a higher energy to a lower energy in energy orbit. Okay, and when that happens, electrons are getting closer to the nucleus, meaning the attractive interactions between the electrons and the nucleus increases, or as a result of that, the potential energy should decrease. Okay, so any answer that says potential energy increases should be up. And when the electrons getting closer to the nucleus, it has less space to move around, therefore they slow down, therefore the kinetic energy, so it has less space to move around, therefore the electrons are going to move faster. As a result of that, the kinetic energy increases. So then the only answer that says kinetic energy okay, oh, give me a second. So I think I eliminated option D incorrectly. Let me correct that. Okay, what I want to say was potential energy decreases. Therefore, I eliminated options B and C. So we have options A and D. Between options A and D, only option D says the kinetic energy increases. So therefore, the correct answer is option D. Okay. So the idea is, again, when the electrons have less space to move around, they move fast. So therefore, the kinetic energy increases. And then the potential energy decreases because the attractive interaction strength increases between the electrons and the nucleus because they are closer to each other now. Right, so that is that. Moving on, which energy level diagram best represents the emission spectrum shown to the right? Okay, this is an emission spectrum. So the first thing we can do is we can eliminate. So emission means you are going from a high energy to lower energy. Okay, so we can directly eliminate option C and D because they show that we are going from a lower energy to a high energy. Okay, so between A and B, what we need to do is we need to determine the energies associated with these transitions. Okay, so we see that transition line A has the lowest or the shortest wavelength, meaning the highest energy, and then line D has the longest wavelength, that means the lowest energy. Okay, so line D should correspond to a small energy gap. Okay, and then if you consider A and B, we see that in A we have a line D with the smallest energy gap. Therefore, that should correspond to the emission spectrum. And on the other hand, line A has a large energy gap. When the electron moves from this high energy to a lower energy in line A, transition A, you have a large energy, because we have a large energy gap here, the energy of the photon emitted is going to be higher, meaning the wavelength should be shorter. Okay, that's why the correct option here is option A. Okay, now that is that. Moving on to question 8. Let's see. In question 8, what we have is, based on the emission spectrum shown in question 7, what types of transitions are occurring. So we see that we know that 400 nanometers is violet light, and then 700 nanometers is red light, red, violet. This is the visible region. Okay, so this is between 400 and 700 nanometers. These wavelengths are within the visible range. If we use visible light or UV or visible light, they induce electronic transitions in matter or in molecules. So whatever the species, therefore the correct answer is option A. Okay, moving on to question 9. What is the frequency in hertz of the highest energy photon in the emission spectrum shown in question 7? The highest energy photon is over here with the shortest wavelength, and then the frequency is given by the speed of light divided by the wavelength, and that should be 3 times 10 to the power of 8 meters per second divided by the wavelength, which is 491 nanometers, but we need to convert nanometers to meters to match with the units of speed of light. And to do that, I'm going to multiply by 10 to the power of minus 9, because that is how many meters we have in a nanometer. So nanometers cancel out, meters cancel out. We're going to get the answer in hertz or per seconds. And then that value, I mean, if we just leave the numbers here for the moment, 491 multiplied by 10 to the power of 8 plus 9, 17 per second. Okay, so I'm going to eliminate options A and C now. Now we are between options B and D. And what we need to do is we need to divide 3 by 491. If we divide 3 by 491, let's see. So if we divide 3 by 500, okay, then you're gonna get 6 times 10 to the power of 14. You can do this in a calculator, but I'm trying to do this in my head because I don't have a calculator with me right now. So if we divide by 500, you're gonna get 6 times 10 to the power of 14. If you divide by 491, which is less than 500, then you should get a number greater than 6 times 10 to the power of 14. Okay, so right now we see that in option B, that number is less than 6. In option D is greater than 6. So I'm going to go with option D over here. Okay, or you can do this, you can solve this exactly using a calculator. I just used that. I just approximated the value, and based on that, it has to be option D. All right, so with that, let's move on to question 10. In question 10, which of the following is true regarding titanium and zinc ions or zinc atoms? Now, if we go back to the first page, titanium is over here, zinc is over here. We know that when you go across a period, okay, we are going across a period, the size of the atom decreases. Okay, so size wise, titanium must be larger than zinc. Why? You're going to have more protons in zinc. As a result of that, the electrons in the outermost shell will be attracted strongly to the zinc nucleus compared to the titanium nucleus, making the electron cloud smaller. And as a result of that, what is going to happen to the ionization energies? Zinc is going to have a higher ionization energies because you're going to have stronger attractive interactions between the nucleus, positive charge, and the electrons. Therefore, you're going to have to provide more energy to remove electrons. So keeping that in mind, moving on to the question, the atomic radius of zinc is less than titanium. So we can eliminate options A, it says greater, and options D, it says greater again. Okay, it should be less than titanium. And the first ionization energy of zinc is greater than titanium. So that is correct. And option B. Option C is incorrect because it says the first ionization energy of zinc is less than titanium. No, it has more protons, meaning electrons are tightly held by the zinc atom compared to the titanium. Therefore, you're going to have a higher first ionization energy. All right, so correct answer is option B. Okay, that is question 10. Moving on to question 11. Zinc oxide contains zinc in the +2 ion form. The electron configuration of this ion can be expressed as, so the electron configuration of zinc 2+, that's the question here. Okay, zinc 2+. Now, if you go back to the periodic table one more time, okay, so we have zinc over here. To get to zinc, we need to fill 1, 2, 3. The third shell is completely filled. That means we're going to have the argon core shell. Okay, and then in the fourth shell or the valence shell, we see that these 4s electrons are completely filled. It should be 4s2. And then in 3D, you have 10 electrons. Okay, in zinc. And therefore, if we have zinc 2+ is zinc, okay, and we know that outermost shell in zinc is 4th shell, so 3D10 and 4s2. Therefore, when you remove electrons, the electrons are first removed from the electrons from the shells furthest away from the nucleus because they are weakly held. Therefore, the 4s electrons will be removed first. Okay. As a result of that, the zinc 2+ will have the argon core shell and 3D10. 4s2 will be gone. Okay. So going back here, the correct answer should be option D then. All right. So moving on to question 12. Consider the following electron configuration of different atoms in various states. In which atoms are electrons in the highest potential energy state? Okay. So now the idea is further away an electron from the nucleus, high the potential energy. Why? When it is further away, you're going to have weaker attractive interactions between that electron and the nucleus. Weaker the attractive interactions, higher the potential energy. That's the idea. Okay. Now, if you consider all of them, all this electron configuration, the 4th shell seems to be the highest shell. We have 4th shell over here and the 4th shell over here, and these guys do not have any 4th shell. This seems like a ground state, so that is out. That's going to be the lowest potential energy. Option C is an excited state. 2p electron has been moved to maybe 3p over here. So, but still, the third shell is the highest shell here. Okay, but when it comes to options A and D, we have electrons in the fourth shell. And then if you think about what we have here is 4p in option A and 4s in option D. Therefore, we know that when it comes to electron energy levels, if we can draw something here, if this is our energy, 1s will have the lowest energy, then 2s, then 2p, and then we have 3s, 3p, and then 3d somewhere around here, and then we have 4s, and then 4p, and so forth. So 4p is furthest away from the nucleus, therefore it's going to have the highest potential energy. So we have an electron in the 4p in option A, therefore that must have the highest potential energy electrons. Therefore, we're going to select option A. Okay, so moving on to the next question. Question 13. Titanium exists in an ionized form in sunscreen. From the PA spectrum below, identify the ionic charge of titanium found in sunscreen. So again, so what we have here is titanium with 18 electrons, is that right? So 2 plus 2 is 4 plus 4, 4 plus 6 is 10, 10 plus we have 8 now, that means 18 electrons. Altogether, we have 18 electrons. Okay, that means if you think about titanium, if you go back to the periodic table over here, let me erase these for the moment. So titanium is over here. Okay, its electron configuration is, it has the argon core shell because it is completely filled up to argon, and then we have 4s2, and then in 3d we have 2. Okay, so you see that in argon we have 18 electrons. Okay, so now what we have in this 4 electron spectrum is 18 electron. Okay, so if you write this again, this is argon and 3d2, 4s2 is the electron configuration of titanium. Now what we do is we have the argon electron configuration. This is the argon electron configuration. So that means we have removed all the electrons from 4s and all the electrons from 3d. That means we have removed altogether 4 electrons. That means it's going to have 4 more protons than the number of electrons, meaning it's going to have a +4 charge. Okay, that's the correct answer for that. Okay, so moving on to question 14. This happens to be one of the questions that got the lowest correct answers. Okay, now if you think about this, now we are given an IR spectrum here. You are told that this is an IR spectrum, and then based on the wavelengths here, we know that this is this is 500 and this is 400, and then that means this should be violet light, and then somewhere else. So this is in the visible region, and then we're going to have these guys in the ultraviolet region. Okay, so because we know that the visible light has a higher energy than the infrared light, one should have the highest energy out of 1, 2, and 3 because it is in the visible region. Well, actually, this is actually in the UV region, but anyway, UV visible light has a higher energy than the infrared light. Okay, and as a result of that, one should have the highest energy, meaning the shortest wavelength. Now, if you compare, if you look at these options A, B, C, and D, it cannot be C because C has the in C and D we have one with the longest wavelength. Therefore, those two options are out. And now between A and B, we now have the shortest wavelength for one, which is correct. Now we need to go to the infrared spectrum to solve this. Now, what we notice here is in between 2 and 3, 3 has a higher wave number. Okay, in other words, 3 has a higher energy than 2. If it has a higher energy, then it should have a shorter wavelength. 3 should have a shorter wavelength than 2. Then in other words, we can say that 2 is the longest wavelength, out of the 3 options. So the only option with 2 with the longest wavelength is option A. Therefore, we're going to select option A. Okay. Yeah, that's the way to think about this. So if you're still worried about 2 and 3, how we decided that. So here what we have is the wave number. Okay, wave number or nu tilde is 1 over wavelength. Okay, that means higher the wave number, shorter the or lower the wavelength. Okay, so 3 has a higher wave number, meaning it should have a shorter wavelength. Therefore, between 2 and 3, we select, we need to have a shorter wavelength for 3 compared to 2. That's how we decided on that. Okay, so that's why the correct answer for this question is option A. Okay, so that is question 14. Moving on to question 15. Given the mass spectrum of zinc to the right, how many isotopes of zinc are there? We see that we have 1, 2, 3, 4 peaks in the zinc atom mass spectrum or zinc mass spectrum. Therefore, we should have 4 isotopes. That's it. So that's the answer. Okay. Moving on to question 16. Which statement is true given the potential energy versus distance graph for the 2 hypothetical covalent bonds? So if you just look at these bonds over here, okay, we have excess with the lowest minimum or lowest potential energy minimum. That means XX bond should be the strongest. And also, the minimum for XX occurs at a shorter distance. Here's the distance, because this is the distance. So the distance between the atoms is smaller when we have the XX minimum, meaning the bond length is shorter for XX. Okay, because the distance at the minimum gives you the bond length. So that is going to be this much for XX, and for YY is this much. So definitely YY is longer than XX. And also, give me a second, XX is shorter. So anything that says XX is longer is going to be out. Okay. And then also, which bond is stronger? The stronger bond should have the strongest attractive interactions between the 2 atoms, meaning the lowest potential energy. So the excess is stronger than YY because you have lower potential energy there. So therefore, we're going to go with option D. That's the correct answer for that. Okay. So that's how we tackle the multiple choice questions. So let's move on to next page. Pre-response 1. Which of the following molecules is likely to produce the infrared and the mass spectra shown below? Okay, so and then we need to justify our answer. Okay, so let's think about A. Okay, so in A, you see that there are no OH bonds in A. Okay, no OH bonds. Okay, if you in the IR spectrum, we see that we have OH bonds. We do not see that there. So, and also CC bonds as well. Okay, there are no OH bonds or no CC bonds. Therefore, option A cannot be our answer. Okay. And then between options B and C, all the bonds are there. CC bonds, CH bonds, CO bonds, and OH bonds. All the bonds are there. However, we know that we have another piece of information over here, and that is the molar mass information. So I can, oh, there you go. So molar mass wise, we see that I would pick, okay, 41, 2, 3, 4, 5, 6. 46 as the molar mass of this compound, 46 grams per mole. Right? And if you look at, if you calculate the molar mass of option B, we have carbon over here, and then the common bonding pattern of carbon is fulfilled by carbon hydrogen bonds. We need 2 of them over here. So we have 4 bonds. Now we have 2 carbons, that means 2 times 12, plus we have 6 hydrogens, 6 times 1, plus 1 oxygen, that is 16. If we calculate that, so we see that 2 times 12 is 24, 24 plus 6 is 30, 30 plus 16 is 46, which is great. Okay, B, so we have all the bonds. Okay, bonds and the molar mass. The molar mass match. Therefore, B is great. Okay, and option C, we have again bends are carbon, so carbon carbon. The common bonding pattern is fulfilled by carbon hydrogens. Okay, and if you calculate the molar mass for this, 2 times 12 plus hydrogens, we have 6 again, 6 times 1, plus we have 2 oxygens as well. That means 2 times 16. Okay, so we have 24 plus 6, 30, 30 plus 32, 60, it's going to be 64, right? So which is much greater than the molar mass of the entire compound based on the mass spectrum. Therefore, option C is out. Option C, the molar mass is too high. Molar mass is too high. So I explained why I eliminated options A and C and kept only B. All right, so that is that. Moving on to question 2. The OH bond has a vibration transition at approximately 3100. What is the energy that energy of that transition in kilojoules per mole? Show your work, no credit. Okay. Anyway, so what we're given is 1 over wavelength to be 3100 per centimeters. That means the wavelength is 1 over 3100 centimeters. Okay, but what we need to do is we need to convert this to meters. To do that, I need to multiply by 10 to the power of minus 2, because that's how many meters we have in a centimeter. So we're going to get the wavelength in meters. Okay, and then to calculate the energy of 1 photon, we need to use this equation, and is equal to hc over lambda, and h is 6.626 times 10 to the power of minus 34 joules seconds, multiplied by c, which is 3 times 10 to the power of 8 meters per second, and divide this by the wavelength, which is 1 over 31 okay, 1 over 31 times 10 to the power of minus 4 meters. Okay, and then if you do that, you're going to get the energy per photon. And then the question is asking you to calculate the energy in kilojoules per mole. Okay, so to do that, you need to divide this by 1,000. Okay, divide this by 1,000 to convert this to kilojoules, because that's how many joules you have in a kilojoule. And then you need to multiply this by the Avogadro's number, because that's going to give you the energy of 1 mole of photon. Avogadro's number is 6.022 times 10 to the power of 23 per mole. Okay, and if you do this calculation, I mean, you can do in stepwise if you want to. You can calculate the energy per photon first and then do it. And but if you do this calculation, let me see. Okay. You're gonna get 37.15, around 37.15 kilojoules per mole. 7.15 kilojoules per mole. Okay, so the most important thing here is to remember to show your work. Okay, I showed how to convert the wavelength, and then and calculate the energy from that. Okay, and then also there's another way of doing this. Let me actually point that out. And let me see that. Okay, I'm going to point that out too. Both are valid, by the way. So let's say that we just use this equation. Energy is equal to Hc over lambda, or Hc times 1 over lambda. Okay, or in other words, we can rewrite this saying energy is equal to Hc times nu tilde. Okay, now what we do is we just plug and chug. It's going to be H is 6.626 times 10 to the power of minus 34 joules seconds, and then C is 3 times 10 to the power of 8 meters per second, and multiply this by the wave number, which is 3100 per centimeters. But the thing is, we need to convert this to per meters. Okay, so let's try to do that. What I'm going to do is I'm going to write the conversion factor here. So we have 100 centimeters in a meter. Now I have, if you look at the units, okay, so centimeters cancel out with per centimeters, and then meters cancel out with meters, seconds cancel out with seconds, and you're gonna get the answer in joules. Okay, this is gonna be the energy per photon. So let's do that actually. Okay, so because it's just multiplication we have here, we have 6.626 times, I'm going to do the exponents separately. 6.626 times 3 times, let's say 31, is going to give us 616.22. Okay, and then if you do the exponents, 10 to the power of minus 34 times 10 to the power of 8 is 10 to the power of minus 26, and 10 to the power of minus 26 times 10 to the power of 4 from these numbers should be 10 to the power of minus 22. to the power of minus 22. Okay, and that's going to be the energy per photon. This is going to be joules per photon. Okay, you don't have to change this answer here because it's not our final answer. Now, once we have this number, this is joules per photon. What you want to do is you want to multiply this. Let me use a different color now. Multiply this by the Avogadro's number, 6.022 times 10 to the power of 23 per mole to find the energy of 1 mole of photon. And once you have that, you need to divide this number by 1000 because that's how many joules we have in kilojoules to convert this to kilojoules per mole. Okay, and if you do that, then again, I'm going to do the exponents first. Okay, so what we have here is, plug this numbers in. We have 616.22 times 6.022. That gives us 3710.87. And then I'm going to do the exponents. So we have, let me use a different color now. We have 1000 canceling out to be this 3 of 23 here. And then we're going to be left with 10 to the power of minus 22 times 10 to the power of 20. And that is 10 to the power of minus 2 kilojoules per mole. Okay, in other words, this should be 37.108 kilojoules per mole. And that's the other way of doing this. Both are valid when you tackle this problem. Okay, so moving on to question 3. You're given a lot of information here. Para-amino benzoic acid, more commonly known as PABA, is commonly used in sunscreen and cosmetics, but has been shown to do more harm than good for the skin, blah, blah, blah. Below is an incorrect structure. Here's the incorrect structure, okay? And a backbone for the structure of PABA. So here's the backbone, okay? And then what you want to do is, and also we are given the IR information, IR spectra information, okay? You're told that we have these bonds, okay, in our molecule. Okay. Now, first point, that is option A, I'm sorry, the part A, 2 points each. Identify at least 2 reasons why the incorrect structure is incorrect. Okay. Now, first of all, the first thing I notice here is, okay, the structure is incorrect because I see 1, 2, 3, 4, 5 bonds around this carbon. Okay. Violation of the octet rule, or say octet rule violation. Okay, that's a no-go, definitely. And also, there are no carbon-nitrogen double bonds, right? So if you look at this IR spectra, there's no carbon-nitrogen double bonds. Okay, so we can type, I mean, you can think about, we can include this in reason too if you want to. No CN double bonds, okay, because here's a double bond over here, okay, CN double bond. No CN double bonds, CN bonds. Sorry, I need to stick with blue. CN bonds in IR. Okay, and also there are, so we see that we have C double bond O bonds. Where are they? You don't have C double bond nodes. Okay, so no C double bond O bonds, no CO bonds. We only need two reasons actually. And then also, I mean, you are given the molecular formula over here. Okay, we have 7 hydrogens right now. If you look at this, so let me erase this for the moment. Okay, if we look at the structure, if we convert this to this is carbon, 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 and a carbon over here. And if we fulfill the common bonding pattern with carbon hydrogen bonds, okay, and then this should be another one over here. We have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. You see that? 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. But in the molecular formula, we only have 7 hydrogens. So we have more hydrogens than what we have. So I mean, anyway, so we can come up with these reasons like that. Okay, why this incorrect structure is incorrect. So anyway, keeping that in mind, we have to see anyway. What we want to do is now, those are 2 reasons to get 2 points each. And then in part B, we need to complete the line structure to match with the IR data and then the information. So first of all, I need a C double bond O bond, right? So I'm going to include that. So let's say that I'm going to have a C double bond O bond over here. And then I have OH bonds. So here's the only OH bond I could have here. And then we have NH bonds. We're going to need 2 of them here, otherwise it's not going to fly. And then in the ring structure, we can actually complete the ring and let's see how it works out. This is what we have. I mean, I'm going to say this is our line structure. Just to make sure, let's have the carbon hydrogens and hydrogens to make sure that we have the correct number of hydrogens. And these carbon hydrogens, and then that's it. Okay, if we count the hydrogens now, we have 1, 2, 3, 4, 5, 6, 7 hydrogens, which matches with the molecular formula over here. So that is great. So I'm going to stick with this line structure over here. All right, this is our correct answer for question 3. All right, moving on to question 4. Draw the mass spectrum for the molecule shown. Okay, I mean, draw 3 fragments of structures and clearly indicate their masses. Okay, so 3 peaks in the mass spectrum is what we need to do. So what is happening here is, if you have a molecule, the molecule fragments or breaks under the harsh mass spectrometric conditions. Okay, I think the most logical place to break this molecule is from over here. And if you do that, then you're going to get a fragment of CS3. Okay, so I think we can just write the fragments or structures. So I think just writing the CS3 should do it. Okay, let's do it this way. So here's the CH3 fragments. I'm going to have the plus charge because otherwise the mass spectrum detector will not detect without the plus charge. Okay, so that's the idea. So we are going to get a fragment of CS3 that's going to have a mass of 15. Carbon is 12, hydrogen is 1. We have 3 of them. 12 plus 3 is 15. And then we have the rest of the molecule over here. Okay, so this part over here, I'm going to draw it as it is. PR, and PR. Let's have a positive charge here. Okay, and then that fragment would be the other one. And then bromine has a molar mass of, or relative atomic mass of 79.9. Okay, and you have 3 times 79.9. 3 times 8. Anyway, 9, and then 2 carbons, 2 times 12. So this should be 240 plus 3 times 8 is 240 plus 2 times 12 is 24, so it should be 264, around 264. Okay, around 264 or maybe a little bit less than 263.7. Okay, let's call it 264. Okay, 264. If you want to be more accurate, it should be 0.3 times less than that. That should be 263.7. We're going to see a peak for that, and then we're going to see another peak for the entire molecule. We call this the molecular ion. Okay, so if we draw the entire molecule one more time, it's gonna look like this. CH3, let's have a charge, okay, and that should have a mass of 264 plus 15. That's going to be 279. 279. Okay, that's our mass spectrum. Okay, now moving on to the last question. So we have selenium. Which of these structures do you think is most likely to be the form that selenium would exist? Okay, so if you go back to the periodic table one more time, okay, the selenium is in group 6. Here's selenium. Okay, and then selenium has the argon core shell, and then we have 4s2 filled, and then 3d10 completely filled, and then in fourth shell we have P4. Okay, so let's go back to this and then write it out. Okay, so what we have for selenium is selenium electron configuration is argon core shell, 3d10, 4s2, and 4p4. And if you write the electron configuration, so we have, if you draw the 40 electron spectrum, actually we have 4s2, I'm sorry, this is 1s2. This is 1s2 with the highest ionization energy, and then you're gonna have 2s2 and 2p6. Now we have 10 electrons, and then we have 3s2, and then we have, okay, 3p6. Okay, and then we have, let's see, here's that, and we have 4s2, then we have 3d10, and then 4p4. P4. All right, so here's what we have. So in the valence shell, okay, this we have a different color to be nice over here. Okay, this is gonna be the core, and then this is gonna be the valence. Valence is the outermost shell. Outermost shell is the fourth shell. In the fourth shell, we have 6 electrons. Okay, so there are 6 electrons. There are 6 valence electrons. Okay, therefore 8 minus 6, or 2 vacancies in the valence shell. 2 vacancies in the valence shell. Okay, therefore it's going to form 2 bonds. Therefore 2 bonds will be formed by selenium. Okay, and now in A we have 4 bonds around it, that is out, and in B we have 2 bonds, that is great, and in option C we have 3 bonds, that is out. So we're gonna go with this. I think this is gonna be the most likely compound. All right, and yeah, those are all the questions in that particular exam. I hope this helped, and talk to you later. Bye, everybody.